Hello everyone, hope you're doing well. Welcome back to another video of day 9, learning about transformers. Um, so transformers, essentially, they are the essential backbone when it comes to LLMs being used by OpenAI. For example, the ChatGPT that use a transformer. Gemini, it uses another type of transformer. So these transformers are the backbone and what every LLM model used by the providers, and essentially those transformers, they can be fine-tuned and adjusted so based on which the types of transformers and their architecture as well. So I've been trying to understand what transformers are, and I'm using this website called Transformer Explainer, and also I've watched a video on YouTube from three blue one brown, or three brown one blue. Basically that YouTube video, and they have a video about 27-minute video about transformers and how they work. So let's get into it. So basically, if you don't know what's going on, let's just first read the text and get to understand one by one. So essentially, uh, what is a transformer? The transformer is a core architecture behind modern AI, powering models like ChatGPT and Gemini. Introduced in 2017, a paper which is called "Attention is All You Need," if I'm not mistaken. But it's revolutionized how AI processes information and then predicts the next word uh, from the context of the sentence. The same architecture is used for training on massive data sets and for inference to generate outputs. How here we use ChatGPT 2, small, simpler than newer ones, but perfect for learning the fundamentals. So this is a ChatGPT 2 architecture, and we're going to learn more about it from start to finish. So now, how transformers work? They aren't magic. They build text step by step by asking what is the most probable next word that will follow this input. So it basically tries to predict what the next word is based on the sentence itself. It learns from that sentence and also on the past data set, the memory that it stores as well. So it can use it for reference. And then, based on what it's learned on the context of that sentence, it will try to gather information or relationship between those words altogether and then predict the next word. So here it says we can explore how a trained model generates text. Write your own text or use an example, then click generate to see an action. If the model isn't going to try another example. So these are examples. Let me try. Artificial intelligence is transforming and then now it's going to generate, as you can see, it's happening, transforming the way. So it's 52%. So we'll get more into it onto how they got the word way, but let's see. Transformer architecture has three main parts. The first part is embeddings. It turns text into numbers. The second part is transformer blocks. This is a mix of information with self-attention head and refine it with an MLP block. MLP is multi-layer perception. So we'll look into it more later on. And the third block is the output, which is the probabilities, determines the likelihood of each next token. So embeddings, the transformer block one, we have many blocks. Apparently, we have 12 blocks of these transformer layers and neurons. And then we have the output, which is one single probability, shows that what is the probability percentage of that word occurring in the sentence. So now let's move on to the embedding. So what is an embedding? Before a transformer can use the text, it first breaks down the text into smaller chunks or units or tokens and represents each as a list of numbers or vectors. Now this process is called embedding, and the term can refer to both the process and the resulting vector. In this tool, each vector appears as a rectangle, and hovering it over shows its size. So if I zoom in on the embedding, so now this is the embedding. So we have the word art. It will break down that word art, uh, artificial intelligence. So you can see it broke down artificial intelligence, that it broke down artificial. So that's a fragment of what is called as token. So that art is now a token. The official is also another token. And they assign those two into an ID, which is called, the ID number is 8001 for art, 9542 for official. So now, token embedding is now an ID is associated with this word art, and official for this number. Now, it's the 768 is a number or the vector size. Um, and essentially, what happens is Each of those words associated with the token ID, that's an embedding, because storing that word. Think of it as like a drawer. You're storing that word into a drawer and you close it, and that drawer has its own number outside of it labeled. So now, plus you can see there's positional encoding. Positional encoding is like a position, like a for we know that art positional coding will be zero, and for official one, intelligence two. So there's an encoding for this one, and then yeah. So this is basically the embedding block, um, token embedding, and this is an ID assigned with it. So let's move on to the next one. Token embedding tokenization splits input text into tokens, small units like words or characters, parts of words. ChatGPT 2 small has 50,257 token vocabulary, each with a unique ID. In the token embedding step, every token is matched to a 768 number vector from a large lookup table. These vectors are learned during training to best represent each token's meaning. So as you can see, total size of the ChatGPT 2 has 50,257 tokens. Tokens are like those words I told you, these tokens, these words. Now, from this, they have made a library, a vocabulary list or lookup table to look at, and that vector size is 768. All right, so 768 columns, okay, from a large lookup table. And what happens is that when the transformer goes into this multi-head self-attention, these words, each of them are referenced with that 768 lookup vector to know whether that word is belonging to it or relevant to it, so that once it does do that the calculation, the processing, it will then be able to compare with itself and see how it will best learn or represent that token with each other, the meaning of it. So yeah, that's basically the meaning of it. Now, positional encoding is word order matters in language. Positional encoding gives each token information about its place, its sequence. ChatGPT does this by adding a learned positional encoding to the token's embedding, but newer models may use other methods like ROPE, which encodes position by rotating certain vectors, all aimed to help the model understand order text. So basically, to assign an ID, we already have an ID assigned, the token ID, but also you want to make sure that ID stays in that place, and then that sequence. And this is the traditional way. But nowadays, newer models or newer LLMs, the architecture of that is basically they're trying to have that the location of that token ID to be rotating it with other token IDs. So to rotate that vector for each process calculation in order for it to be learning it. And ROPE is another terminology and technology concept about it as well. But yeah, so that's the embedding block. Now we have the transformer block one. We have 12 of these, but they're basically multi-head self-attention. So multi-head self-attention is basically what tokens share information with each other. So the first word art, and then second is official. They learn from each other. Then intelligence, then is transforming the. So that key aspect of it is learning information about it in the multi-head self-attention block. The MLP, the multi-layer perception, is what it basically receives that information or the learned representation from the multi-head self-attention and refines it, makes it better or polishes it, each token's detail. Model stack many blocks so token representations become richer as they pass through GPT-12 small has 12 of them. Right, so there are 12 of them and they go through this repetitive process. Multi-head self-attention is basically lets the model decide which parts of the inputs are important, relevant to each token. This helps it create capture meaning and relationships even between far apart words. In multi-head form, this model runs several attention processes in parallel, each focusing on different patterns in the text. So basically, what happens is that in this block, the multi-head self-attention block one, it basically decides which part of the input texts or the token IDs are having that most relevant to each other, or the relationship with each other. So make sure it captures that meaning, even if it's far apart. And basically, this happens in parallel, right? So it's running this process in parallel, on different patterns of the text. Query key value. This is basically the token embedding is transformed into three new embeddings, which is a query key value. This transformation is done by applying different weights and biases to each token embedding. These parameters, weights, and biases are optimized through training. Once created, queries compare with keys to measure relevance, and this relevance is used to weight the values. So essentially, what's happening here is these embeddings are then gone into three sub embeddings. So, for example, art will go into key, art will go into query, art will go into value. Same thing for all the other words. And then there's then after the activation of those neurons, then there's going to be a weight assigned to each of those token, the meaning of it, right? The information, the number of that weight of each token. And then you're going to do a dot product multiplication with the query and key. When you do that, you get bias. The bias is added, and then you do the activation to get the weighted sum average, weighted sum of the weights and biases from those two, and they're added up. So you can see art with art is 1. Art with official 0.93, because it makes sense if you combine art with official, it's artificial. So but if you do art intelligence 0.64. So that's what's happening. All right. So queries and key, they're compared to see how relevant they are with each other, the words, and then that is used to weight the values after that. Multi-head, you have 12 of these. So yeah, just focusing on smaller set, grammar, meaning, or long range. You can have many of them, and they're running in parallel as well. Mask self-attention. So mask self-attention is a model decides how much each token focuses on others. Dot product is a multiplying matching numbers in query key vectors. Sum to get attention scores. Mask is hide future tokens so it can peek ahead. Softmax converts scores and probabilities, each row summing to 1, showing focus to early tokens. So this attention block here is basically the dot product of the key, which has its own token ID, and that token has its own weight number. That is dot product with another embedding query, which has again its own token and its own weight, and that weight is then added with a bias to then give you the weighted sum of both of them, and then that sum is basically gone to an activation, which is softmax activation. This converts those logits into zeros and ones basically of how well it relates. So art, we know art and art matches, it's relevant, so therefore it will be 1. It's so this is dot product. You get minus 3.65. Then you do scaling masks is like uh, kind of remove any filtering to make sure it doesn't peak ahead, and then you have conversion softmax between zeros and ones, right? So you're squishing it. So this is what's happening. Then attention output and concatenation. Then each head multiplies its attention scores with its value embeddings. So now it will multiply the output with the value embeddings to produce its attention output, a refined representation of each token after considering context. It has 12 such outputs, which are concatenated to form a single vector of the original size 768. So now the output, we can click on and see how it does. This is the output. So you can, let me click on it again. So this is the attention. We can see 6 by 6, right? So attention we saw for art was 1, right? It was very the probability is 1, meaning it will be very dark, and if the value is close to 0, it'll be very like light gray or white-ish. So you can see 6 by 6 matrix multiply with the value 6 by 64. Therefore, with the value of these words embeddings, we have the output as art. So if I just hover over it, for example, here, I can see the tension 1, art times art here is giving me this at this position. And then if I go down, now it'll take on this attention, official, and then yeah. So this now refines this output representation even more for the official. So yeah, this is what's happening. Moving on, we have the multi-layer perception. So the multi-layer perception is basically the output, what goes to it to refine the token its representations. A linear layer changes embedding values in size using the learned weights and biases. Then a non-linear activation, I believe it's a ReLU, decides how much each value passes. So okay, so they're using GLU. I don't know what's GLU, to be honest with you. ReLU is a rectified linear unit. So it's a linear rectified weights and biases that it takes in from the output as we saw here. And then it converts that any weights and biases that are negative, it will be okay negative. But then if it's after greater than zero, positive, then it's going to be uh, linearly growing. So if you, for example, click on it, where is it? MLP multi-layer perception, GLU. Okay, click to see the MLP process. So this is the MLP expansion. So this is the embeddings, right? Then we have the expansion weights. So now these are the weights of them. The expansion bias, we have the biases, and then the expanded of them. So for example, if I hover over here, I can see the art embedding. We multiply it with the expansion weight plus the bias, and then this is the output of it. So yeah, this is the formula as well, and you do it for each word. And then the GLU is the one that rectifies it, giving you the strong patterns as well. Output logit. After all the transform blocks, the last token's output embedding, enriched with a context from all previous tokens, is multiplied by learned weights in a final layer. This produces logits, 50,257 numbers, one for each token in GPT-2's vocabulary. That indicates how likely that each token is to come next. So as you can see, token ID 835, that was also here. We can see token ID. Oh, it's different. It's 8001. Um, yeah, sorry, way is a different word. Yeah, so different word. So basically the output of that, it's the logits are then you do a softback activation, or you convert that into probabilities, and then that's going to give you the ID token that is used from the 768 vocabulary, and then looks into and see that this word it makes sense. So if I expand it, so this is the logit, and then the temperature, I'll get into temperature later. Then you filter out, and then you have the softmax here. You add them all of the other words and you get 52%. And they do the same thing for this word, for example, world. So the world has minus 101.05, and then you do the exponential, and then you get 42%. So yeah, so that's that. Next up, probabilities. Logits are just raw scores. To make them easy to interpret, we convert them into probabilities between 0 and 1, where all add up to 1. This tells us the likelihood of each token being the next word. Instead of always picking the highest probability token, we can use different selection strategies to balance safety and creativity in the generated text. Temperature. The temperature is basically adjusting or fine tuning the output and the probability of that being a highly next predictable output. So, of a higher temperature, meaning that it will only, I believe, focuses on that word. So, if I do 5, now it focuses 27% on this word being way. If I increase it even more, so now it will focus on 23%, 17%. If I sorry, so basically it's opposite. So if I reduce lower the temperature 0.2, it basically reduces the other possible options, as you can see here from the list of the predictions. So it only focuses on the highest percentage, which is this one, 70%. But if we increase the temperature, then we're making it choose account for other predicted percentage probabilities of that word as well. So make sure it removes any. It makes it more creative as well for the outputs. Sampling strategy is a sampling. You sample out, you filter out top 5 results, and then you shuffle again. So it exists to get most likely tokens. Top P keeps a small set whose total probability is at least P, trimming unlikely ones early. Then softmax turns the remaining logits into probabilities, and then one token is picked at random from the allowed set. Residual connection. Transformers have auxiliary features that enhance the model's performance. For example, a residual connection that adds a layer's input to its output. keeping information from fading through many blocks. In GPT-2 is used twice per block to train deeper stacks effectively. So residual connections are what the connectors, that they use between the input and output, and to make sure the information is kept there and transmitted throughout the whole process. So residual connections, uh, yeah. Okay, before I get into it, this is the key query key value formula. So the embeddings that we have here, we multiply with the weights of the query key value, or it's RGB, red, green, blue, and then the bias of that. So you do the weighted sum, right? So embedding ID time the weights plus bias, you get the QKV, V for the word Azure, and yeah, so it goes through each of them like this. So that's that. So now the residual connection, talked about it. We have layer normalization. Layer normalization is basically helps stabilize both the training and inference by adding input numbers so their mean and variance stay consistent. This makes the model less sensitive to its starting weights and helps it learn more effectively in GPT-12. It's applied before self-attention, before the MLP, and once before the final output. So if I click on the layer, can I click on the? No, I can't. Yeah, layer normalization is basically from the name itself. It stabilizes the output, both the training and the inference, by making sure the input numbers are like consistent and not like like very far off scale. So making sure that the weights and biases are also aligned. And yeah, it's applied twice, one before the self attention and one before the MLP block. Uh, yeah, and then last but not least, we have the dropout. Dropout is basically a neuron that is turned off, or some connections between numbers so the model can learn and not overfit. So to prevent our model from overfitting to specific patterns, this helps it learn features that generalize better. GPT uses it, but newer LLMs often skip it because they train on huge data sets and overfitting is less of a problem. And inference, dropout is turned off. So yeah, dropout is basically turning off some connections, some neurons, and then turning on some others, and it's like each process it will choose a random one turn off. So in order to remove any biasness or overfitting, the model can kind of gain doing training as well. And yeah, that's mainly of a transformer. I hope I didn't do a good job explaining it. Essentially, going deeper into detail as well. But this is the website I found a visual understanding of it. Of course, I would need to repeat and revise the video on three blue, one brown, or three blue, one brown video that has chapter 5. What is a transformer? I highly recommend watching it. And yeah, that's it for today's video. Thank you for your time. Take care, stay safe, and till next time.